Hi, my name is Branko, and I was recommended by a friend to start a yoga class. But before I went, I wanted to see what it's like. So I have a friend named Hebe. She has a yoga class, so we're gonna go check it out.
Okay, ladies, take a deep breath and breathing.
Hi, how are you guys doing?
Hi! You want to join my class?
Great. No, looks cool. Do you mind if I tape it and see what it's like first?
Oh, sure. What's your name?
My name is Branko.
Hi, Branko.
Hey, guys.
Hello.
Hey.
Welcome.
Hey.
Okay, so let's just keep it. Okay, 1, 2. Okay. You guys relax now. A little bit. Okay. So today I have a new position that's called downward facing dog. So you want to try that?
Yeah, sure.
Okay, so we can try that. Okay, let's start it. It's like this.
That seems really hard to do.
And then the angle should be 90. Did you get it?
Oh my god. Yeah, it's a cool position. Is there any real force that the floor exerts on each hand or foot?
Oh, I think so. That's a good question.
What about friction force?
It should be friction force. You guys want to try to find it?
Sure.
Yeah,
Can you
sure.
show
Okay, you can
us?
join us.
Okay, great, cool.
So in order for us to find the forces, we need to take some measurements first. And Branko and Megumi are going to demonstrate that for us.
Okay.
Go ahead.
Okay, great. Megumi's in the downward facing dog position, and we measure from the bottom of the foot to the top of the leg is 40 inches. And then with her back straight, we measure from the top of the leg to her head, which is 27 inches. And then from the top of the head to her fingers is 13 inches.
Okay, that's perfect. We'll figure out the formulas.
Okay, this is a diagram for the downward facing dog position. A good trunk, the length is 1 or 2 centimeters, and then trunk to the head is 122 centimeters. To find the distance from foot to head, I flip the triangle and make like this. So this square and this square should be this one square. That's why I found 159 centimeters for here. And then to find the angle here and here, I can use tracing. So 159 times sine. Okay, so 159 times sine theta is 122. So theta equals 50. So the angle here is going to be 50. So I add those two, 50 plus 90, and then subtract from 180 is 40. So this angle is going to be 40.
Okay, so to find the value for x1, first we need to multiply 102 centimeters times cosine of 50 to get the value of x1, and x1 was 65 centimeters. To get the value for x2, we subtract x3 minus x1, which was 159, minus 65 centimeters to get x2, which equaled 94 centimeters. And now Kim's going to explain to you how the normal force for the hand works.
Okay, so in order to find the normal force that the floor exerts on each hand, you have to use this formula here of the torque to find out the answer. And then the weight, her weight was 121 pounds, and that's equal to the force, which is 53.9 kilograms. So here is the normal force of the hand, and here's the distance, x3. Okay, so here we're going to move to this diagram here. This is the distance from the foot to the hand in that position, downward facing dog. And then the weight, her weight was 121 pounds, and that's equal to the force, which is 53.9 kilograms. So here is the normal force of the hand, and here's the distance, x3. Okay, so here we're going to move to this diagram here. This is the distance from the foot to the hand in that position, downward facing dog. And that's equal to 159 centimeters. And here, there is a 65 centimeters from what my friend Shaq got over there. And the 94 centimeters also. So here, I'm going to apply these numbers to this equation. So again, back here, the normal force times the distance from the foot to the hand, which is 159 centimeters, minus the weight of the lower body, which is 213 newtons, times the distance of the x1, which is this little part here, minus the weight of the upper body, which is 320 newtons, times the x2, which is 94 centimeters, and then you come up with the 350 newtons as the normal force of the hand.
Okay, so now the normal force for the hand was 350 newtons. That was for both hands, but for each hand it's 175 newtons for each side of the hand. And now I'm going to show you guys how to find the normal force for the foot. First of all, the formula for it is normal force of the foot plus normal force of the hand minus the weight of the legs minus weight of the trunk, which equals to normal force of the weight leg plus weight of the trunk minus normal force of the hand. And to apply the numbers then, all we have to do is normal force equals to 750 newtons minus the normal force of the hand that she found earlier, and that would equal to 400 newtons for both feet, and which would make each foot equal to 200 newtons, and that is pretty cool.
Okay, we just solved for the normal force of the foot, but now we want to find the sum of the torques around the hip of Hebe here. So this is Hebe's leg. It's 102 centimeters long from the hip to her feet. Okay, and we know that the center of mass is 41 centimeters from the hip here. That makes this length 61 centimeters. Okay, to solve, we know that this angle here is 50 degrees from the earlier part, and we need to solve for this height here. And to do that, we use our trigonometric identities. We know that the sine of 50 degrees equals x over 102. Solving for x, we know that x equals 79 centimeters. Okay. We also need to find this length from her feet to where the center of mass goes to this point here. And we do that using the trigonometric identity, cosine of 50 degrees. And solving for x, we find that that length is 38 centimeters. Okay. Now that we know these measurements, we can solve using our sum of the torque equation. And Lisa's going to do that for us.
Okay, torque is equal to 0 because Hebe's in equilibrium. This is a definition of torque on a rotating axis. When it's rotating counterclockwise, it's going to be positive, and when it's rotating clockwise, it's going to be negative. Therefore, frictional force is positive because her leg is pushing down in a counterclockwise position, so it's positive. Height is given, we know that's 79. Normal force is negative because it's pushing in a clockwise position. Y is given. Weight, we know, is 213 because that's also given. And 27 is this distance, which is 65 minus 38. We just plug it all in, and we just do step-by-step simple algebra, and then the final answer is going to be 256 newtons for both feet, so one foot is going to equal 128 newtons. And then, Bronco, do you want to explain the frictional force on the arm?
Yeah. We found that the frictional force on both feet is 256 newtons. And since this frictional force of the feet is equal to 256, we use another equation called the sum of the forces in the x direction equals 0. And since we know the frictional force of the foot is 256, this Hebe is in an equilibrium, so we know that the opposite force has to be negative, and the sum of the two forces have to equal 0. So we know, as a result, the frictional force on the hands is also equal to 256.
Okay, good job, guys. We now have better understanding for the position, right?
Right.
So you guys want to try that?
Sure.
Okay, so go ahead.
Let me see. Does it look like this?
Like this?
Yeah.
What was it? I forgot.
Okay, perfect. That's good. Like facing more like down. Yeah. That's perfect. Okay.
Does it look like we're at 90 degrees?
Yeah, pretty much. That's good. So you guys feeling friction force, normal force.
Oh.
Okay,
These forces hurt.
good.
Okay.
Yeah.
Okay.
Did you guys have?
Hi, my name is Branko. I'm in scientists, not technicians.
Hello, my name is Hanli from Scientists Not Technicians.
Record.
I'm Megumi.
And I'm Lisa, and we're from Scientific. Yay!
Hi everyone, I'm Shao from Scientists Not Technicians, and I hope you guys enjoyed our presentation.